Just a quick reminder about the flux. If F is a continuous vector field, and you have an oriented surface like S, with unit normal vector n, then the flux is the surface integral of F over S. Surface integral of F over surface S. The double integral F dot ds, I'm going to use bar on top of S because we're going to represent this by a vector, and this is S, just giving the surface to you, is equal to the double integral of F dot n ds over S. Recall that the double integral of F dot ds over S can be written as the double integral of F dot, this ds is the cross product between Ru and Rv divided by its magnitude times the element of integration over the surface. This guy can be written as the double integral. Let's just convert the whole thing into u and v, substitute the whole thing. So now we're going to take the integral over the region of, very good. You have f of r in parameter u and v dot ru rv divided by its magnitude, and ds is the magnitude of Ru cross Rv dA. So we can simplify these two, and this guy can be written as the double integral over d of f dot Ru cross Rv dA. So remember this formula when you're working with a parametric surface. You have all of these nice formulas to utilize here. A quick example for you: compute the flux. Find the flux of the vector field given to you as z, y, and x across the unit sphere. Very good. So as usual, we're going to apply the parameterization. X is equal to, since you have a unit sphere, you have 1 times sine phi cosine theta. Y is 1 sine phi sine theta, and your z is 1 cosine phi. And theta ranges between 0 to 2 pi, and phi is in between 0 to pi. We don't have any restriction over these. So if you substitute phi and theta into the function, your function becomes f of phi and theta is equal to, your z becomes cosine phi, your y becomes sine phi, sine theta, and your x is sine phi, cosine theta. Very good. So this is this part, and then dot the cross product between RU and RV. So R phi cross R theta. We saw this guy from previous calculation is equal to the vector sine squared phi cosine theta sine squared phi sine theta, and finally you have sine phi cosine phi. Very good. Now you're going to find the dot product between these two, f of phi and theta dot r phi cross r theta is equal to, so the multiplication between these two, you get cosine phi sine squared phi cosine theta plus, here you have sine to the third phi sine squared theta plus sine squared phi cosine theta and cosine phi. Let's try to simplify this. Here you have sine squared phi cosine theta cosine phi, so it becomes 2. Okay, so we are taking the double integral 0 to 2 pi, 0 to pi of 2 cosine phi sine squared phi cosine theta plus sine cubed phi sine squared theta d phi d theta. So for this integral, you can separate these, and also for this integral, you can separate this. This guy becomes the integral 0 to 2 pi. Here you have, let's write 2 outside, cosine theta d theta times integral 0 to pi. Here you have cosine phi sine squared phi plus, now for this integral, here you have 0 to 2 pi of, we don't have any theta here, so d theta integral 0 to pi. Sorry, this is sine squared theta d theta and integral 0 to pi sine cubed phi d phi. This integral is sine, it's going to be 0, so this part is 0. Now, if you compute this integral, you need to convert this into the double angle, and then compute this integral sine squared sine phi, and then sine squared becomes 1 minus cosine squared. You use u sub, and as we saw before, as I did the computation, it becomes 4 pi over 3.